Okay. Uh, Bismillahirrahmanirrahim and Assalamu alaikum to all my students. And this might be the last lecture of our course of artificial intelligence. And as I promised, so this chapter is about gaming in general, so that it will just, because this is in your mind that we will study something about gaming. So now this is the stuff that is for your gaming ideas. So without wasting any time, let's start. And I hope that you are seeing these slides. So the chapter is basically the adversarial search. Now you can imagine that you have to put something in your mind that if your agent in a word is trying to do some planning or trying to do something, you can say, then the other agents at the same time are trying something against you. And so the actions of your agent and the actions of other agents in the same environment are in the world, you can say, are in conflict with each other. I will explain this idea more with the passage of time. So when agents are in conflict with each other, then this is the environment which is the competitive environment, you can say. So in this environment, agents are basically doing what? Agents are basically doing competition with each other. And their goals are surely in conflict, because all the agents are trying to achieve the same goal. So that's why the goals the goal is in conflict. And that's why it's called competitive environments. And the other name for this competitive environment and the agents who are performing actions are who are performing searches in these kinds of environments. The other name for this thing is adversarial searches. And also we can use the name games for these searches or for these environments, because game is the same thing in which one or more than one agents are trying to achieve some same goal, and the goal is in conflict. And also the environment is very much competitive. So this is something that you can understand as adversarial search that we are now going to understand. And in this chapter we will cover something about games first, and then we will see how can we make optimal decisions in games. And lastly, we will study two algorithms regarding this adversarial search, or regarding this gaming or competitive environment, whatever you want to say. We will see these two algorithms at the end, or you can say from the middle to end. So let's move on ahead. So this is something according to our planning. So this is something games, and in this topic we will try to understand the definition of the game. Or you can say that, okay, games is a problem, then how you can define this problem. So this is a question very much related to your chapter number 2, where you defined many different problems in some specific format. mainly you have to define 5 different things: initial state, actions, transition model, goal state, or something like that. So here the same kind of discussion is now you have to do for games. And for games, we know that we must have some initial state, and that can be called as S0. And what that initial state will specify, or what that initial state will give us, we know that initial state is some kind of a state of a game that explains the setup of the start, or you can say how the game is set up initially. What is the beginning point of the game, you can say. So that is something initial state. So then players into S, which means that at any state S, which player has the move. So you can define, for example, if there is some player John and there is another player Ali, so then you can write John, and if the state is maybe state number 9, so, and then you can write John into 9. So which means that now the state number is 9 and the John has the move actually. So this is very much simple. So player into S defines which player has the move in state S. And similarly, actions into S uh, at any state S or in a state S, actions into S is something that returns the set of legal moves which are available at that state. Similarly, if you have a graph and there are many actions moving out of that, if you have a node in a graph, and if there are edges moving out of this node, then these edges moving out of this node is something, the actions that you can perform from this node or from this state. So this is the same concept uh, at any state or in some specific state. If you are considering some example, so in a state, the possible number of actions or the legal move that you have at that node is something that you can represent with actions into S. And then this is the result S comma A, which is saying that if you are in a state S and after performing some action A on this state, where you will go. So what will be the result? This is simple. So maybe some other state, some other next state. So that is something transition from one state to another state. So that's why it's called transition model. Um, so that's why it's called transition model, and it defines simply the result of a move from state S with action A. So it is also something that you already have studied in previous chapters. So I don't think that it is something very much difficult concept for you. I don't think so. So then terminal test or the goal test, you can say. So a terminal test at a state S, for example, if you have to check this goal test at maybe this is according to the strategy, but I am saying maybe at any state during your searching. So if you are at any state S, then you can check that either you are on a terminal state or not. And this terminal test or this goal test will be true when your game would be over. So which means that when your game will be over, then this terminal test at that state would be true and false otherwise. We will see. So we will see, because first you will see some brief algorithm that is called Minimax algorithm, and that after that you will see some complex algorithm that is called Alpha-Beta Pruning. So we will see all these things, and finally the utility, and then S comma P. So So utility function has a different names you can see. So utility function is a function that will calculate the value of the cost, or simply the value at that state for some player, you can say. So utility function can also be called as objective function, as you can see from this slide. The other name for utility function is payoff function. So all these have the same name: utility function, payoff function, objective function. So all these are the different names used in the literature for the same thing. And what it is, it defines the final numeric value for a game that ends in terminal state S for a player P. So if the game process is at the end, and if at that state some player P uh, has the turn or something, so then you did, and if you apply, if that state is something, the leaf node are the state which is describing that the game has been ended. Okay, so now the utility function comes into action, and it will calculate the some value or the numeric value for this game which has been ended for that player P, and then it will return that value. So this utility function is responsible to calculate uh, the utility value, the objective function, or the payoff value. So now moving further, now this is the, so from this discussion, we have studied initial state, and then we studied action functions, and then result function. We have seen these three concepts. So these three concepts, very similar to your concept in chapter 2, very much similarly defined the problem, basically defined the game tree, defined the problem state space, you can say. So if you have these three functions, initial state, actions, and result, then you can define a game tree. I will use the word game, and then now I will not use the word problem, because previously we were using this word problem, but now here we are very much specific to adversarial searches, so that's why I will use the word game. So if you have these these three things, initial state, actions, and result function, then you can define the whole game tree, or you can say then you can define the whole game state space. And in this state space, as you are seeing on this slide, you are seeing that there are some states given here for the game Tic-Tac-Toe, or you can say noughts and crosses. So here, these states, this is one state, this is also one state, similarly this is also one state, and all these blocks, not blocks actually, the squares, the complete squares containing 9 squares. Actually, this is one complete square containing 9 subsquares. So this is one state, 2, 3, 4, 5, 6, and so on. So these are the states. Or you can say, if I consider it as a graph, then this is the node, and there we have the edges, and we have further nodes underneath this node. So nodes are basically the game states here, and the edges that we have here are basically the moves. And this is a simple example for the tic-tac-toe game, and we will see its detail next. However, just a brief note. For example, this is the root node, and initially we have an empty state, and after that we have how many possibilities. So now it's the turn of a player. The name of the player is Max, and the other player name is the Min. Max has to mark the X mark, and Min has to mark the letter O, you can say. So Max has to mark the letter X, and Min has to mark the letter O. So initially it is empty. So first it is the turn of Max, and how many options for Max are available? 1, 2, 3, 4, 5, and so on, 9. So 9 options are available, which you can say. So Max can mark here at number 2, at number 3, at number 4, 5, 6, and so on. And similarly for Min, only for this option. Otherwise, all these nodes have its corresponding options or positions available, but we are only considering this first one. So how many positions are remaining? 3, 3, 6, and 2, 8. So now it is the turn of Min, and Min has to type the letter O. And then how many positions are available for the Min? Only 8. So you have to make 8 states here. 1, 2, 3, 4, 5, and 8. And then you can write that Min can mark O here, or at number 2, or 3, or 4, and 5, and so on. So initially it is 9 states, and then 8 states under each game state. This is one game state, or under each node. And then this node will also contain 8 under it. This node will also contain 8 positions under it, and so on. And then after that we have, again, it is a turn of Max, and now Max has to mark the letter X. And now for Max, there are only 7 positions are available. So as you are seeing here, so 1, 2, 3, 4, 5, and 7. And after that, Min has to mark the letter O, and for Min, 6 options or positions are available, and so on. And if you will do the things like this in this way, then finally maybe you will reach at some states like this. So this is something terminal state. And here you are seeing that Min has the winning position. So that's why the utility for the Min player is -1, because it is trying to minimize the objective of the Max player, and Max is trying to maximize its objective. So that's why the value that we are using for the Min is -1, and for the Max we are using it +1. And if there is a position that Min is winning the game, then the utility value for that state is -1. And if the Max player has won the game according to this position, then the utility function will give us the value +1. And if the game is drawn, then you will receive the value 0 from the utility functions. So this is just an explanation of this picture, so that you will not feel difficulty in next slides. So let's move on. So now this is something, if you will look over here, so the first topic was games, and after that optimal decisions in games. So now game is over, and then now we are moving toward the optimal decision in games, but there are some concepts involved in that topic, so we should have to understand those things first. This topic is labeled as simple approach in tic-tac-toe. Now you will understand this simple approach quite easily because you have seen this uh, figure here in quite detail. So if we build a simple algorithm, so this is a tic-tac-toe game, or the other name is nodes and crosses. So you have to mark the cross and then nodes is for 0 and crosses is for x. So in a very much simple algorithm for the tic-tac-toe game, you have to do what? You have to calculate all the possible moves from current position, any current position. If you are at a root node, then the all possible moves from that root node is these 9 moves that player max can perform. And this is something that you have seen here. So in a simple algorithm, what you can do, you can calculate simply the all possible moves as you are seeing here. Then you can expand each of these nodes. Maybe you have to focus on the slide because I am highlighting something by using this cursor. So what is the next step? Next step is that you have to expand all these nodes one by one with its further possible moves. And we know that the further possible moves for this node is 8, for this node is again 8, and so on. For all these states or nodes, the further possible moves positions uh, are also 8. And what you will do next, you will continue this expansion until you will have a winning position for the player. But with this simple approach, if we will continue for expanding the moves again and again and again, so definitely we will reach at some winning positions. But that winning positions, I would not say that it is only for one player. I will get a series of winning positions. I will get a series of winning positions, as you are seeing. So just remind it that at the initial state, there is only one state. After that, I have 9 options in the next level, as you can see from this slide. And after that, I will have 8 positions underneath each node. So 1 multiplied by 9 multiplied by 8. And at the next level, I will have 7 options available underneath each node. So you can multiply it by by 7. And then at the next, I will have 6. So this is some kind of a factorial. So if you want to write it in totality, then you can write it in this equation as you are seeing on this slide. So you have to sum up summation 0 to n is equal to 8. So this is something 0 to 8 is the number of positions available at each level. And then you can write, okay, 9 factorial. This is this one because maximum is the 9 available. So factorial of 9, and then you can write, okay, n plus 1 just to make it 9. N plus 1 and factorial. And after that, you will have 0.9 million almost entries, as you are seeing 986410 number of positions that you have to search, or that you have to calculate, or that you have to visit in a simple algorithm. So you can imagine that this is a very simple game, tic-tac-toe game, just 9 positions in one state maximally. And if you have to build this game, and if you will apply the very much simple approach, very much like brute force approach, then you have to consider these numbers of zero. 0.9 million almost number of positions that you have to evaluate. So by the way, in current days of technology, this is not a huge number. But for example, we can imagine that for such a simple game, we have to compute such a huge number only for this. This is not a huge number, but as far as the size of the problem is concerned, this number is huge. And by imagining this scenario, then you can think that if you have to build some state-of-the-art game, then it is very much difficult for you to go on with this simple approach. So that's why your algorithm for gaming must be smart. Otherwise, it is very much difficult. So this decision, so this optimal decisions, how can you perform, or how can you apply, or how can you do this optimal decision in your games? Because we know that an optimal strategy always gives us such outcomes which are at least as good as any other strategy existing around us. And so just to understand it further, for optimal decisions, put it in your mind that if you want to implement the strategy of optimal decisions, or if you want to implement uh, this technique of doing optimal decisions in your problems or in your games, then you must have to include some evaluation function, or you have to include some heuristic function, as you are studying previously from chapter 3. So without heuristic function, you cannot do something better. So for example, consider a two-player game, and we are saying it is zero-sum game, because in this game, if one player has achieved something, then that would also become the loss of the other player. So in zero-sum games, players are trying to achieve the same goal, and if one player has achieved a part of that goal, for example this thumb, then this is a loss for the other player. The other player will not ever achieve it again, because this has already achieved by the other player. So that's why we are taking this simple example of zero-sum games, so in which gain of one player is balanced exactly by the loss of other player. And for this, we are introducing some static evaluation function, which you can represent it with f of n. And this is the definition of this evaluation function for this zero-sum game is that you have to calculate complete rows, columns, and diagonals, open positions for the player X. So if I can rephrase it for your understanding. So you have to calculate the open positions for the player X or A for complete rows, columns, and diagonals. You have to count it first, and then you have to count the open positions for other player B or O, again for complete rows, columns, and diagonals. And then you have to take the difference, and that difference would be, you can use as a static evaluation function for this zero-sum game. And you will get some value as you are getting here on this slide. The higher the value of this f of n means that you are more close to the winning position. Okay, so let's try to understand it. So first, and then we will move on to the next slide. So here you are seeing that this is the first state, and here Max has marked X 2 times and O, and Min has marked O 2 times. And now this is, here it is the move of, here it is, Min has performed the action, and at this level, Max has performed the actions. So now, I am giving you the real understanding of this f of n. So here, you have to compute the complete open positions for X. First, you have to count the open positions for player X or B, and you have to count complete rows, complete columns, complete diagonals. For example, for X, this is one possibility. So this is one row. Here X is not able to make a row. Here X is not able to make a row. So only one. And then, okay, here X is not able to make a row. X is able, so this is 2. X is able to make a row in future maybe. So this is 3, and then this diagonal is 4. So there are 4 possibilities for the player Max to make rows by writing X in it. So this is 1, this is 2, and then 3 and 4. So here, that's why you can see 4 here. You are seeing 4 here. So this 4 is, so this 4 is basically what? This 4, I can use annotation here so that the people, yes, I can, just a moment. So this 4 is the complete number of open positions available for complete rows, complete columns, and complete diagonals here on this state. And 2 is the complete number of rows, columns, and diagonals, open positions for the other player. So here, this is the column where the other player Min can make a line, and this is the row where this player Min can make a line, and there is no any other diagonal or something available. So that's why it is -2. So 4 minus 2 is equal to 2. So now the value of the f of n is 2. And similarly, you have to count these values for this state. So 1, 2 for diagonal, 3 and 4 is for the max. And here Min is not able to make a column, but Min is able to make a complete row. So that's why this is only one available. Diagonal is also not available. So only one is available. So 4 minus 1 is equal to 3 is the f of n for this state 2. And then similarly, 4 minus 2 is for this thing. You can calculate it by yourself by using the same strategy. 1, 2, 3, 4 minus this one and that one. So 2 and so on. And 3 and 3. So as you are seeing, so 3 is here. 3 is here also, and 3 is here. This is something higher value. So three higher values are available, but only this one maybe, only this one is the state in which the player max is winning. How? For example, if, for example, this is something X has moved here. So now it is the turn uh, of min player. So min player can either mark it here, or here, but only once. So if the min player will mark it here, okay, it blocks this row, but the max player can write something here and can win the game. So this is a state where the player max can win. But for example, these states have the same value 3, but it is not something a state in which X can win this game. It is very much simple. The main player can simply write O here, write O here or notes here, can make notes here, and then can win the game. Similar situation is here. So in these three states, all have three values, but the max player has only the first state in which he has the option to win this game. Or you can say this is the situation where the max player is winning, but in these situations max player is not winning. So now this is the question. So static evaluation function is good in computing some value, but static evaluation function is not giving us this answer that which player is going to win. So this is something you have to keep in your mind. So from 3, one thing is sure, from higher values, one thing is sure, that we are near to the completion of the game, or we are near to the winning positions. But the question is still something which is remaining, that which player is going to win, we don't know. According to the algorithm, we don't know. According to this static evaluation function, we don't have an answer for this question yet. So let's move on to the next slide and then see something. So first I have to clear the drawings. Okay. So this first point, higher the result of f of n, the closer the move towards a win. This is something I have just already discussed. And here, the second point is also I already discussed, that f of n is useful. Useful in what manner? Useful in these manners, that f of n is telling us, if f of n has a higher value, then it is telling us that the game is very much close to the winning position. But it does not provide us this answer that which player is going to win. So we don't have an answer for these questions. So to handle this situation, we must have some other heuristics. We must have some other heuristic, or we can use some other heuristic in addition to this f of n. So this f of n is useful, but we have to use some another heuristic which is necessary to pick the move with the highest f of n while protecting against a loss in the next move. So this is also one thing. So what we have to do, if two players are trying are gaming with each other, so f of n is giving me this information, or giving this information to both of these players. F of the value of the f of n is telling to both of these players that either you are near to the winning position or not. And these players can identify that either they are near to the winning position or not. They can identify this thing from the f of n. But they cannot identify. But for example, if this player has done some move, if this player has done some move, how much good this move was and how much loss has happened to this player, I don't have any answer for these questions by using this f of n. So to get the answers of these questions, the Minimax algorithm is given next in upcoming slides, and this algorithm is explaining that when one opponent is trying to maximize its objective, at the same time the other opponent is trying to minimize its objective. Or in other words, if algorithm's opponent is trying to minimize whatever value the algorithm is trying to maximize. So now you can read from this point number 3 here on from the slides that Minimax algorithm is something in which the algorithm's opponent, you have your program, you have your game, and then there is an opponent of this game. If you are playing this game with the computer, then computer is something, your algorithm, you can say, you can suppose, and the person who is playing on the computer is basically the opponent. So Minimax algorithm is in which the algorithm's opponent will be trying to minimize whatever value the algorithm is trying to maximize. So if your computer is trying to maximize its objective, if your computer game is trying to maximize its goal, at the same time your opponent is trying to minimize your goal. So that's why this algorithm is called Minimax. So the idea in this Minimax algorithm is simple, that we should allow our opponent to do the least damage. Either it is the computer or either it is the opponent. Every user or every agent will try to give or to leave those options for its opponent through which he or she can make the least damage. So this is basically the idea of the Minimax. Now we will see here you can see that after 3 slides we will move on to this Minimax algorithm, but before that we are again trying to get some theoretical stuff of this Minimax algorithm. So Minimax can use one of the 2 basic strategies. In Minimax, you can either search the whole game tree or you can define sub depth first, and then you can search up to that depth in the game tree, and then you can evaluate your states accordingly. So you can, in Minimax algorithm, either one of these strategies can be adopted. So in Minimax algorithm, you have to perform the search operation, or you have to pursue the uh, tree or tree the tree of your game. So you can pursue or you can search the tree, but you have to make some conclusions or you have to make some guesses first that how your opponent will play, how your opponent will play. And after making guesses or judgments about the situation of your opponent's play, then you can pursue that tree. For this, you can use the cost function for this evaluation, and then you can evaluate how your opponent is likely to play. So that is something, again, very much uh, informative. So you can use some cost function. It's a very much similar concept that you have studied some heuristic function, objective function, payoff function. That is something you can take it as the same thing. So you can use some cost function, and through this cost function, what you can do through this cost function, you can evaluate that how your opponent is likely to play. When you have a word likely, then you can say that you are computing some probability about probability of the opponent's action, or probability of your opponent's play, that how my opponent will play. You are computing some kind of probability. So that's why the word likely is here. And you can use some cost function here. And then you can use some probabilistic approach in your cost function, or without probabilistic. So let's move on. So what you have to do, if you are at a current state, you have to look ahead a number of moves. Are you have to, if this is your level n, or if this is a state at level n, you have to see next state at level n plus 1, n plus 2, n plus 3, and so on. You have to evaluate some number of moves ahead, and then you have to apply the cost function over it. This is the explanation of the previous point on this slide. So then you have to apply the cost function over it, and you have to compute the total value from this level n to n plus 1 or 2 or 3 and so on. And when you have the value for that player, and similarly you can have the value for other players, and then you can finally decide that which move is going towards the goal. If you have, and then you can maximize the value of your move. And when you are maximizing the value of your move, it is at the same time minimizing the value of the opponent moves. So this is basically the procedure in the procedure of the Minimax algorithm. So in Minimax algorithm, first it is being said that you can search the whole game tree, or you can just define some depth first, and then you can search up to that first. So it is up to you. So you can do something like that, and then this is theoretical discussion that you can just pursue the tree. You can search the tree, but how you can search the tree? You have to make some guesses about the opponents, and how you can make these guesses about the opponents. Then here you can use the cost function. That how you're, and using this cost function, you can calculate that how your opponent is likely to play. So this was the last function. And this discussion continues, and it is giving you further idea that you can, if you are at a current position, you can look ahead a number of moves, and then you can calculate the cost function up to that move, and then you have to do this task for all players, and then you have the values, cost values for all the players, and then you can examine and that which move is the best, which is moving towards your goal, and in this way you can maximize the value of your move, and at the same time it will be minimizing the value of the opponent's move. So this is basically Minimax search uh, procedure, and we are now going to see this procedure. It is not something very much complex, so we will see it. And but one thing, that it is also the part of the other algorithm that is coming up here on this last slide. It is the part. So now it is up to us. Either we can run this whole Minimax algorithms completely, and then we will leave these concepts when it will be repeated in the next algorithm of alpha-beta pruning. So let's see what will happen. So this is function Minimax. So look at this function. So the name of the function is Minimax, and it is taking some state n, and it is taking some state n. Is begin, and this is the beginning of the pseudo code, and here we are checking at that this state is deep enough. Here deep enough means leaf node. Keep this thing in your mind. So deep enough means leaf node, or you can fix your depth as you said here, in these points. You can fix some depth, or you can search up to leaf nodes, the entire game tree. So it is up to you. So if n is deep enough, then return the estimated score of this leaf. Then if your state is the leaf node, or if your state, so I am using the leaf node. I am using the term leaf node because I am searching the whole tree, and I am not defining some depth first, and then I am not searching for that depth, like limited iterative deepening depth first search, like that. So I am not going to perform some operation like that. So I am in this Minimax algorithm, I am searching up to the leaf nodes. So I can take this deep enough means leaf nodes, and then return the estimated score of this leaf. So I have to estimated score here. Here the utility function will be applied, and it will give us some value for that state. So for this, consider it as your example. Consider it as your example. So this is the partial example tree, not complete. So this is some state which is given to us here. Min has marked O thrice, and similarly max has marked X 3 times. And next, this is the max turn. So here, this is the level to mark X. And here, this is the level to mark O. And these are some terminal states highlighted in bold. So you can consider it as a partial example to understand this Minimax algorithm. So this is now my N. So this is now my N. Okay. So N is going as an input to this function, and n is not a leaf node. It is not a leaf node, as you are seeing. These are the leaf nodes. So, and this is not, for example, this is a given state. So this is not a leaf node. So I will come here at the else portion, and here let n1, n2, and nm be the successors of n. So n is what? N is what? N is this node. And how many successors? 1, 2, and 3 positions are left. So 3 successors, n1, n2, n3 are possible after this state. So this n1, n2, and n3. Okay. Now move on here. So n1, n2, n3 be the successors of n. Yes, we have some 3 successors. Now we are checking. If n is a min node, then I have to use this return statement. Or if it is not a min node, then I will come here in the else portion and I will use this return statement. So, okay. So what is my n then? So this n is for the max. Here it is max. It is written, which means that now it is the turn of max to write x here. And here now, whose player's turn is here at this level? Then min. So this n is belonging to max. So n is a min node? No. N is a max node. So I will come here. Return max, minimax n1, minimax n2, minimax n3. You are calling this function again by putting each successor node in it, n1, n2, n3. I am not writing it on the board because it is not so much complex. So I am just moving verbally over this algorithm. So what will happen? So this is something minimax n1, minimax n2, minimax n3. And then afterward, this state will be selected. For example, here, minimax n1, minimax n2, and so on. So then it is n1 will be called with node n1, and you will check it again. N1 is deep enough. It is a leaf node. No, it is not. So you will come here again, and then you will decide some successors of this n1. What it means, come here. So this one, Minimax n1. And how many successors? 1 and 2 are available. 1 and 2 are available. So just a minute, and I will come here. So where were we? Okay. So Minimax n1 will be called. And again, it will be checked that we have some successors, n1 and n2 for this node, but it is checked that this n1 is a min node or max node. It is a min node. So then it is a min node. Just a moment. So it is a min node, and the min node, then this statement will be executed. Return with minimax n1 and n2. So here you will get some values, and then minimum from these values will be returned. And in this statement, you will get some values, and then maximum from these values will be returned. I can explain it in detail, but I am hoping that this is your last chapter after the completion of this whole semester. So you must have this understanding in your brain or in your mind, actually. So, but I am feeling that maybe you will get some difficulty. So I don't know. I should have to explain it on the board or not. Okay, let's take an example. Let's take an example on this board. I will try to. So keep this algorithm in your mind. So first condition is I will check that the node is a leaf node or not. If it is a leaf node, then I will return the uh, value for that cost value for that node. And if it is not a leaf node, then I will come to the else condition, and I will first infer the successors of that node, how many successors it has. And then afterward, I will check that the node, the parent node, is a min node or the max node. If it is a min node, then I will calculate the minimum by using this recursive calls. And if it is a maximum, then I will calculate the max by using these recursive calls. That's the end. So now I have to stop sharing so that you can see this board actually. So suppose that this is the root. Oh, I have to make a little bit bigger. And I have to see. So this is basically here XX, and we have this condition already, and this is the max. Okay. So just okay, Ji. So this is the root node actually, and this is my node, the first one, the N node. So in the algorithm, I will check this N node will be passed, and you will check that either this N is a deep enough or is a leaf node. No, it is not a leaf node. So what will happen? I will next I will check how many successors it has. It has 1, 2, and 3 successors, 3 vacant positions. So 3 successors. It will have 3 successors. But first, it will have 3 successors. Because this is mentioned in the algorithm that I have to compute successors of this node. So these are the successors of this node. I can also write it as like this one. I can write the entry that is as it is 0, 0, x, x, 0, and x. And now in the algorithm, what I will check next that this n is a min node or a max node. So this n is a max node. I have mentioned here. This next level is the level of the main player. So this n is a max node, and if it is a max node, this is not a main node. I will come into the else portion of the algorithm, and in the else portion of the algorithm, it is mentioned here that I will use the return statement, and I will use the return statement, and I have to compute maximum. But first, there are some recursive statements for these nodes. So these are basically the nodes, and I can call it N1, N2, and M3. And this here I have to, and here for these I have to calculate, I have to find the max, I have to find the maximum by using this. This is one recursive call, Minimax N1. This is another recursive call, Minimax N2. This is another recursive call, Minimax N3. These are three recursive calls. I can show you again your algorithm because I don't have too much trust on your minds. Sorry for these things, these wordings. Just a moment. Yes, share screen, and then here. Now you can see this n is not a leaf node, and you will come to this. Now look over the slide, and then you will come over this L portion, and here N1, N2, and N3. This N1, this N2, and this N3 are the successors of this N. And if N is a min node, this N is a min node. No, it is not a min node. So you will come to this else portion, and it is written here, return max, and then minimax N1, minimax N2, and minimax N3. So I will compute the max, this max, according to this slide, this outer max. So this something I have mentioned outer circle, and I have written maximum. So I have to find the maximum among these three recursive calls. Minimax for N1, this one, minimax for N2, and minimax for N3. So, but I don't have a value yet because it is a recursive call, so the tree will expand further. So this has further two options. Now I'm stopping this sharing because so this has further two vacant positions, which is the positions for the next successors. So this is minimax N1, so it will be called. When it will be called, the algorithm will iterate again, and first it will be checked. This is a leaf node. No, it is not. So then you will have to give the successors, and this is, for example, I am writing. So this is something, your successors. Okay, I am writing the values again as, oh sorry, here you have to write. So if this is the max, so max can write X here, and then max can write X here, and then max can write X here. Okay, now O can write, this is X already, this is something done according to previous steps. These are the two positions. This one, this one, this one, this one. These are the two positions. Sorry. So two successors. And here min can write O here, or min can write O here. maybe you are not seeing, but maybe you are getting idea, so it's okay, not issue. Values are not something important. Actually the structure of this iteration is important. So this is something minimax n1, and when you will call it, first it will be checked this n1 is a leaf node. No, it is not. You will check the successors, so these are the successors. Then you will check that this n1 is a min node. Yes, it is a min node. It is written here, it is a min node. When it is a min node, then you have to, if it is a min node, then you have to calculate the minimum. Then you have to calculate the minimum according to the algorithm. Then you have to calculate the minimum, and this is something minimax. Again, this is something minimax n1 or n11 you can write, just to distinguish from this previous one. And this is minimax n12 you can write. Similarly, you will do something for that one. So here there are two. Here you have two options again. And similarly two options again here. And you will keep on doing this until you will reach at the leaf nodes. And now I will go directly to the slides. And when you will reach at the leaf nodes in the algorithm, the condition of leaf node will be checked and it will be returned with the utility value. Now I will go directly to the slides and I will show you. Okay. So maybe I have to share the screen. Yes. No, it is okay, I think. So now it's okay, I think. So now I have a look over this algorithm again. So this is n is deep enough, which means leaf node or what, and then you have to return the score of that node. And then it is else portion. You are checking the successors, and then you are checking that a node is a min node. If not, then it is a max node, and then you have to apply this max statement, and then it is end minimax. So in this way, you can imagine that if you are a first root node, then this is your root node, and then you are checking from the slide that n is not a leaf node, then else you are just inferring or extracting the successors of it, as you have seen. Here I have extracted these three successors. And then again, look over the slides. Then again, after extracting those successors, minimax n1, n11, and minimax n22, and minimax minimax n1, minimax n2, and minimax n3. You are calling this function again, and then you are checking it again for the n1. If it is a leaf node, yes. If it is not a leaf node, then you are again checking its successors. And what you are doing, you are opening the tree, levels of the tree again and again until you reach the leaf nodes. And when you will reach the nodes like this one, so you are opening here on this slide, you can see after this root node, you can open these three successors, and then by using minimax recursive call, and then after that, this is the successors for this minimax n1. These are the successors for Minimax N2. These are the successors for Minimax N3. And after that, here, wherever you will reach at the leaf node. Your leaf node statement in the algorithm will be executed and it will give you the utility value. Next, you will get the successor for this node, which is on the board. On the board, I have mentioned it with N11. So it is up to you. So you will get leaf nodes actually. And when you will get leaf nodes in the algorithm, you will use the utility function. And utility function will give you the value. And we know the utility value for the max is +1. Utility value for the min is -1. Which means that the min has won the game and its value is -1. When max will win the game, the value would be +1. And if the game is drawn, then the value would be 0. This is something we already studied from some previous slides. So now, if this n is in the algorithm, it will be checked that if this n is a leaf node, then return the estimated score of this leaf. So for example, here, if this is a leaf node, and nobody has, neither max neither min has won the game, so the value for this state is 0. So this 0 will be returned to this one, previous state, because it is a tree and the calls are recursive, and you can understand that each call, when it is called some function, after the completion of this function, that value will be returned to the previous call. So this 0 will be returned to this previous state. And similarly, this here, the max player is winning. So that's why utility value score is 1. And this 1 is returned here. I will show. And this is the level for max. And this is the level for min, which means min has. And this is the level for max. So max has the level. Max will get maximum value. So there is only one value, so that will be returned. And here the max will get maximum value from this level. And here it is only one leaf node, so that value will be returned. But these are the two children of this min node. And now this min will get minimum value. Keep this in your mind. Will get minimum value. And from this 0 and 1. And from this 0 and 1, what is the minimum? 0 is the minimum. So 0 will be backed over or returned to this previous node. Or you can say previous call. Similar is the concept for other one. So this is something, the leaf node, and here min has 1, so -1 is the utility value. And here this is the leaf node, x has 1, so this will be returned to, this is the max node. So max will get maximum from here. So 1, it is only one node, so 1 will be returned to this level. And from this -1 and from this 1, this min will get minimum value, and -1 is the minimum. So this one will, be returned to this state. And similar is the situation here. But here from the 0, -1 and -1, this is the max. This is the max player, and max will get the maximum value. This -1 is not the maximum value. 0 is the maximum value. So 0 will be returned here. So this is the execution of this Minimax algorithm. And it is not something difficult. It is only, I don't have a proper whiteboard or else, otherwise I can explain it to you very easily. However, I have this paper and I am showing you the full execution of this partial example by using this Minimax algorithm. I can show you this page by stopping this sharing. So now you can see. I don't know. So this is the that root node which I was displaying on the board, and then these are the same. This is the N1, N2, and N3, and you have to calculate maximum from these three, and these are the further successors according to the algorithm. According to the algorithm, and here you have to calculate the minimum from this one, and then minimum from this one, and then minimum from this one, and then next successors according to the diagram that is available in the slides. That is available in the slides. I can just explain it in a bigger way so that you can just view it. You can just view it. This is something I have already done, but I am facing some kind of difficulty in explaining to you. So anyhow, this is simply you can just see, and you can just brainstorm yourself on that, on this page which I have just shown you. And now I am moving forward. So this is the Minimax and this is the partial example. Okay, sorry, maybe I didn't share the slides. Yes, now it's okay. So this is the partial example tree for the Minimax, and now we are moving forward towards the actual topic, alpha-beta pruning. So one thing is sure, in Minimax algorithm, if this is a root node, you are expanding nodes from left to right in this tree. Or you can read this algorithm and the same thing is happening. And then you are expanding nodes from left to right, but in a depth first search, which means that, okay, after this node, these are the successors, but you have selected this one and you applied Minimax over this one. And after that, you will get these successors, and then you will apply Minimax over this successor. And after that, you will get this successor and you will apply Minimax, and then you will get some value, you will come back, and similarly, you will expand the nodes in this way. So you are expanding nodes in this Minimax algorithm according to the depth, or you can say according to the depth first search. And depth first search is exponential, so Minimax search is also exponential. And unfortunately, we cannot eliminate this exponential notation. We cannot eliminate. What we can do, we can just cut the half of the tree or the tree partially. Here, what is the meaning of this cut? Means, for example, if this is the tree that I have to evaluate, and if I will cut this part, if I can use this annotation. So if this is the tree, and if I will cut this portion of the tree, then what will happen? I am not reducing the complexity of the algorithm, but I am you can say, yes, reducing the time logically, not physically. because I am not, this is the part of the tree, but I will not execute this part because this part is not needed. So I am using, now we are going to do some kind of a similar thing like that. You have seen that we will cut a portion of the tree so that it will not be executed, and when it will not be executed, then definitely uh, we will have the less time for the algorithm, and maybe that computation will give us our solution speedily. So let's have a look over those concepts. So Minimax search is exponential like DFS, and unfortunately we could not eliminate that exponential physically, but we can cut the tree in half or partially effectively. And for this we have, and this cutting idea is basically called pruning. This cutting idea is basically called pruning because in pruning we are basically removing some portion of the tree or the parts of the tree, and this removal of parts of the tree is called pruning. And for our purpose, the particular technique that we will use would be alpha beta pruning. Why it is alpha beta? Because there are two variables, alpha and beta, that we will use in that algorithm that will keep the value of something, and that value is very important. And algorithm will go on by updating the values in alpha and beta, and algorithm can also have the ability to decide by looking over those values of alpha and beta. So we will see these things on the coming slides. So when you apply this alpha beta pruning on a simple Minimax algorithm that you have seen previously, uh, then it will return the same move as Minimax would, but prunes away branches. So after applying this alpha beta pruning concept, the algorithm will behave very much similar to Minimax algorithm, but we will see additionally some benefit that the algorithm will have the capability to prune the branches, to cut out the branches, to filter the branches which are not needed in our final decisions. So let's move on. And now we are going to consider two-player game, tree, which is given here on this figure, on this slide. And again, we have two players, max and min. And we will do some optimal decision in this example according to the alpha beta pruning algorithm. And our attention would be now on each point of process. So let's have a look over it. This is not a complete example. This is for your understanding. And here, for example, this upward direction triangle is for the max player, and this downward directed triangle is for the min player. And here this upward means again the max, but these are the leaf nodes, and the values of these leaf nodes are given here. And here it is max. For max, there are three actions, A1, A2, and A3 are available. which are moving towards other state B, C, and D respectively. And then B has three actions, B1, B2, and B3 moving towards leaf nodes having some final values or the cast values. Similar in the case with C, with C1, C2, C3 with final values. For D1, D2, D3 with the final values. So in this example, you are seeing that here from 3, 12, and 8, this min is trying to get the minimum value from these three. So that's why it is 3 here, because this is the level for the minimum player. And for this one, from 2, 4, and 6, 2 is here due to this min player, because min player is wishing to have the minimum value at this node B and C, and respectively for D. And 14, 5, and 2, so this at this node, this 2 value will traverse over here. And from the 3 to 2, this is the turn of max, and max will get the maximum value 3 over here. So this is according to the Minimax algorithm. But just have a focus, just try to understand. If this is the max, for max, if these are the three options available, A1, A2, and A3, what is the best move for this player max at A? The best move is A1. Because by using this move, it will get maximum value. By using this move, it will not get maximum value, it will get 2. And by using A3, it will not get maximum value, it will get 2. So this is this A action A1 is the best for A, because in this way A state will get 3 value. Similarly, for B, when this will be opened, 3 will be here. But when 12, after comparison, minimum player will find that 12 is higher than 3. So it will just throw that 12. And that at will be thrown out in a similar way. And it will keep this 3 from all these 3 states. And in this way, 3 will move on. So what is pruning? If I will say, so I can just discuss over here. The idea of pruning is this, that there is no any need to execute this part of the tree, which is highlighted in red. Why it is not needed? Because after processing of this subtree, when max player has a surety that 3 is surely coming towards me, then why it will accept this 2? Why it will accept this 2 again? So just have a look over it. After opening all these options, main player has decided to get 3 here. And max is, after processing this first branch of this tree, max is expecting 3 value at A. After that, the algorithm will go on and it will approach to the C, and this option will be opened, this 2 will be opened. This 2 is less than this 3 value that A already has. And this 4, this min player would not allow this 4 to come here because 2 is the minimum. This 6 This min player would not allow this 6 to come over here at C because 2 is the minimum. So I am just saying, so algorithm will check this thing that okay, at C the value is 2, so I don't need this 2. So 2, I don't need this 2, but min will decide this 2 is okay. And after first opening this first branch, min player will decide okay, this is the value 2, and then it will check, oh, it is 4, which is higher, so there is no need to give this value further and give this value further to C, and C, and it is decide that it is 2. So there is some logic here. There is some logic here that if this 3 is higher, 3 is higher, and after opening it with C, C will open this 2, and 2 is minimum, and max is also looking that this is 2, minimum is also looking that this is 2. So max, when it is opened for the first time, max is also looking over it. Max has seen that the value is coming from this branch is 2, and max already has 3 value higher than this 2. So max is not going to accept it. And when it is not going to accept it, because min can give minimum value 2 or less than 2. So then there is no need to open this thing. Now, see it mathematically if you are not understanding. See it mathematically. Just I want to clear this annotation first. So point number 1 is just the repetition of our previous concept, that idea of pruning after applying it on the previous figure is described below. This is the pruning idea. And from our previous discussion, we have finalized that there's no need to evaluate 2 successors of nodes C in previous figure. This one, these 2 successors are not needed to be executed at node C. So suppose those 2 successors have values X and Y. Suppose this has values X and this has value Y. Then the value of the root, value of this root A is minimax root. You can see if this is the minimax root, then you are getting minimum of this 246, minimum of 1452, which is written here. Max into min 3128, comma min 2xy, comma min 1452. This is the min level and this is the max level. So this is something written here mathematically. Simplifying it further, max, so minimum 3 will be returned from here, minimum 2 will be returned from here. So 2 is here, but this is something we cannot decide yet. So min 2 into xy is written as it is. If we mention this whole min 2 into xy comma y with z, if we mention z is equal to, if min 2xy is equal to z, then we can write max 3z2. And the first thing is 2, and this is the min. So if whatever the value x and y will be, min will not give any value higher than 2. So min will allow the values less than or equal to 2 only. If the value of y will be 1, min will give 1. If the value of x will be 0, min will give value 0. If the value of x equal to 3, min would not allow because 2 is already available there. So less than or equal to 2 is allowed. So if less than or equal to 2, then this is not needed because max already have 3 here. So 3 is there. So there is no need to, that's why x, there is no need to explore the values of x and y, because that would be certainly less than or equal to true. I don't. So with this mathematical explanation, I am saying that I don't need to explore these values of x and y, because it is clear that it would be less than or equal to 2. And if it would be clear that it would be less than or equal to 2, then there is no need to explore the successor x and y. And now I hope that it would be clear in your minds. So this is just adjectives or properties of alpha beta pruning that you can apply alpha beta pruning to any to trees of any depth, and it is often possible to prune entire subtrees rather than just leaves. So in this example, you are seeing that we are only pruning a small portion, but in some other example, you will see the entire subtrees are pruned. So this idea is for pruning. And alpha and beta. Alpha is the variable that we will use for the max, and beta is the variable that we will use for the min to represent the value, best value for the max and for the min respectively. And now we are going to see the detail next. This is just a figure. You have to look over it first, and then this figure, we will use it as an output for this algorithm. So here it is showing that when alpha beta pruning algorithm will run, it will take some root node after expanding it, and after expanding it further in a depth first search, it will get value 3. This is a 3 value, and this is the level for the min. So the beta initial values for alpha is minus infinity, and plus infinity is the value for the beta. These are the initial values. And after opening the first branch, the min player will get value 3. The value of the beta is updated here. And after that, 12 will be opened. 12 is higher than this 3, so beta will not accept. So beta, the main player will not accept it, and the value of the beta would be remained as 3 according to its previous status. After that, it will be opened, and it will not be accepted because it is again higher than this 3 value that beta already have. And now the children, all the leaf nodes of this B node are processed. So now the values of the alpha and beta are updated accordingly. So the beta value would be 3, and this 3 value can be given next to the level at higher position, which is for the max player. So at this position, max can get maximum, or the best value for alpha is only 3. So this 3 is also updated for alpha 2. Similarly, when you open the other subtree, and when you will open this first branch too, the beta value will be updated, but this is not needed at higher level. And in this way, there is no need to expand the further 2 branches of this node C. And we will come directly to to this nodes D actually in this diagram E. And after opening this 14 here at D, the value of the beta will be updated here. and this is the value more than 3, so the max value would be very happy to accept this 14 value. After opening the next value, which is 5, the beta value will be beta value. Main player will update the value of beta with 5, and player A will also in a position to accept this 5 because 5 is higher than this 3 value. And after opening it with 3, with 2, the value of beta will be 2 here, and here at this level the value of alpha is also 2 here, but this alpha is not needed at this level because 3 is already higher than this value. So one step is skipped here. After the diagram E, one of the step for this branch 5 is skipped here. Okay, not an issue because understanding is clear. Now we will move on, and we will try to reach at the algorithm so that we can run it properly. So alpha-beta pruning algorithm do what? The alpha-beta pruning algorithm does what? We will see. Alpha-beta pruning algorithm updates the value of alpha and beta as it processes the steps of the algorithm, and it prunes the branches at any position where the algorithm finds that the value of the current node is going to be worse than the current value of the alpha and beta. And alpha and beta are for max and min respectively. So when this condition is found, or when this condition is true, the algorithm applied the pruning effect. We have this algorithm next, given next, and now we will execute this algorithm over the same previous example, and then we will see this thing, how it's going on. And after that, this is the lab project, and then it will be the end. So this is, by the way, an important algorithm, and it is also very complex algorithm, like crypto arithmetic puzzles that you already have seen. But I am sure that I will inshallah give you the good understanding of this alpha beta pruning. So first have a look over this algorithm, because then I have to remove these slides and then I will show the board by writing over it. So, but first have a look over this algorithm, that it is function alpha beta search, and it is taking some node, some state as an input, and it will return some action. Initially, we have some sub-algorithms, max value and the min value, that are being called by each other or by this main function alpha beta search. So max value, and here the state, this same state, which is a node, minus infinity is the value for the alpha, plus infinity is the value, initial value for the beta, and with these values you are calling this function max value. This function will be executed, and when this function will return, finally it will return some value in the v, and then we can say return the action in actions into state. At that state This actions will return the set of legal actions available at that state, as according to the notations that we have seen in the beginning of this chapter in the topic of game. So this is something that function that will return the set of legal actions available at that state. And from these actions, I will compare this value v with the actions, and with actions with which this value v will be met, I will return that action simply. So max value will be called, for example, here according to this example, we have this A at the top, then B, and then C, and then D, and then we have A1, A2, A3, and B1, B2, B3, C1, C2, C3, D1, D2, D3 respective actions. So suppose you have state A here, and then function max value state is A, alpha and beta minus infinity plus infinity. This function is called and returns the utility value. It will return utility value. Keep this one. It will return utility value. If state is a terminal state, then return the utility of that state simply. Otherwise, these things are mentioned that you are just v has the value minus infinity, then there is a loop according to the actions available at that state. And normally at state A, we have 3 actions available, A1, A2, and A3. At B, we have 3 actions available, B1, B2, B3. So initially, this loop is going to be executed for 3 times for A1, A2, and A3. But here, again, you have written some max, which is something you are identifying the maximum value. You are concluding the maximum value from here, from this one, and from this one. But this is again min value, which is the call to this function again, So min value result SA. What is result SA? At any state S, you are applying some action A and you are maybe going to some other state. That state would be returned here. You have to write it here, and then this is the value for alpha and beta. You can take these values from here or according to the algorithm. Then we will get some value here, and then we will get some value here. And from these 2 values, you will return the maximum value to this V. And then this V is matched with the beta value, equal or greater. If it is greater or equal, then we will return this V. If it is not, then we will check the value of alpha and this V. And from these both values, we have to take the maximum one and we have to store it in alpha. And these all 3 statements are under this for loop. When this loop will be ended, then we will have a return statement with B. Similarly, the min value has the same statements like we have in the max value, but V with a positive infinity. Here we have a minus infinity, and then we have a for loop F with respect to actions, very much similar to this way. And then we have a minimum here, and here we have a maximum. And then V comma max value here. Here we have a min value. So this min value is calling this function here. So we are calling this function again and again, and you will be mad. Yeah, definitely you will be mad. But I am your teacher, so at the moment I am mad and you are just enjoying. So, okay, enjoy. Your time will come when the exam will come. So anyhow, so max value result, that is the similar that to this one, result SA and then alpha beta. So the other statements are very much similar. Here V less than equal to alpha, here V greater than equal to beta. So beta, alpha, and here we are getting minimum, here we are getting maximum. So now we have seen this pseudocode. And What I can do now, I will write this pseudo code on this whiteboard and then I will execute the values. Now I'm going to stop this sharing so that you will see the bigger screen. So according to the algorithm, first we have the alpha beta search main module, then we have the submodule called max value, and then we have the another submodule called main value. So the main value, the name of the main function is alpha beta, and there we have only one condition, v is equal to max value, which is the call to module, and then we have a state. Initially we have a state a, and then we have minus infinity and plus infinity for alpha and beta. This is the call to the max value function, and we are just drawing the line over here, and then we are writing the max value function, maybe. Just a minute. According to the algorithm, I have another module that is called max value, and here what are the values? A, it is called with a, minus infinity, plus infinity. These are the values for alpha and beta, and the initial node is a. Then in the algorithm, there is a terminal state for there is a condition which is checking that it is a terminal state. If it is a terminal state, then calculate the utility value of that state and return that value. But this A is not a terminal state. So this condition will not be executed. And then I will come to, in the algorithm, I will come to this V, and the variable V has minus infinity according to this algorithm. I can show you that algorithm once again so that you can believe it, what I am doing. So this is the algorithm I am following. I cannot show you because I have to show you this smart board in a bigger view. So you can see this is the algorithm I am following. And I am a minus infinity plus a. I have called this function alpha beta. Max value is called, so I am here at max value. And this is not a terminal state, so it is false, so I am here v with minus infinity. And then after that, I will execute this for loop 3 times with 3 actions, A1, A2, and A3. And these are the 3 statements under it. We will see what will happen. And one statement is calling the other function min value here. So we will see what will happen with us. And I am stopping this sharing of screen again. for the bigger view of this. So my V is minus infinity according to the algorithm. And now I have a for loop under it. And that loop will be executed for A1, comma, A2, comma, A3. These are the three actions available at node A according to the diagram. You can see it by yourself by going back towards that diagram. So these are the three actions available. Where are the, okay, for the moment, I can show you those three actions. So you have to keep that figure in your mind. I will not open it again. So this is the diagram that you have to keep in your mind. So this is A, this is B, C, D, and actions A1, A2, A3 are available. And from B, B1, B2, B3 are available with these values: 3, 12, 8, C, 2, 4, 6, C1, C2, C3, and D, D1, D2, D3, 14, 5, 2. So now I will not show this diagram again. So according to the algorithm for loop, this is A1, A2, A3. And under that, loop, we have this statement. What is that statement? V is equal to max, and then V, and then you are calling another function min val. Oof. So now I will face issues. Now I will face issues due to less space. What I will do. So what I can do, this is something A minus infinity plus infinity. This is something known to us that we have called this function with this value. Now I am changing the direction of the smartboard in this way so that I will use some more space, and I will write the max value function here and the min value function here on this side. So I am removing one more time. Otherwise I can explain it from the paper, but leave it. So max value function. So max value, or simply Maxwell, is called with A minus infinity plus infinity. And then I check that it is not terminal state, and then according to the algorithm we have written something V is equal to minus infinity. So this is something we have written according to the algorithm. And then there is a for loop with actions A1, A2, and A3. Maybe I can write it a little bit ahead, because I will reuse it. So for A1, A2, and A3. And then we have, after that we have this V here. This is something I am writing according to the algorithm, is equal to, then I am finding max for maximum, and then V and then I am calling this min-val function. Again, the space is not too much. There is some function written over here like this, result. I don't know what I'm doing. So I can just move the things back. So I will keep this thing in my mind, that alignment, I have to keep this thing in my mind. So I'm writing from here, V max, then V, then min val result S comma A comma alpha and beta, and then this is close. So this is result SA. This is result SA alpha comma beta. So these are the things I am just writing according to the algorithm, and later on I will write these values. And then after that, there is some value written over here. If V greater than or equal to beta, then return what? Return V. I am simply writing V. It means I have to return V. And then I have alpha is equal to max, and then alpha into V. By the way, these three states, these are under this for loop, but due to space, my alignment is not okay. So you have to consider it. This is under this for loop. This is under this for loop. This is under this for loop. Okay? And then we have a return statement which is returning V out of this for loop, And now we will execute. So my initial statement initial thing is with node A minus infinity plus infinity. V is equal to minus infinity. Now this for loop will be executed. I can write this for loop here. Just for clarity. Now for the three actions, A1, A2, A3. So for A1, now this loop is going to be executed for A1, for action A1, which is going towards node B according to the figure which I have shown you. And I will not show you these figures again and again. So, okay, for action A1, if action A1, then V is equal to max. Here, this V is what? This V is minus infinity. This V is minus infinity. Now it is very hard for me. This V is what? Minus infinity according to this statement. And then you are calling min-val, another module, another sub function
in the algorithm. You are calling min-val. This is another module. This is max-val function or module, and this is minimal. So you are calling, but with what values? First, result from state S with action A. State, what is state? State is A. And what is action? A1. So at A, when you have action A1, you are reaching where? You are reaching at B. You are reaching at B. This is the result of this one. And the value of alpha is what? Value of alpha from previous minus infinity. This is now issue. Minus infinity. Value of beta is what? Positive infinity. Positive infinity. Beta, this one alpha minus infinity, beta is positive infinity. So now I'm going to execute this min val with these values because these values are now finalized. So I am here now. Now it's very dangerous because from this preview maybe I can this hand can erase some content from this whiteboard. Anyhow, let's see what will help, what will come as a help to us. So main value, and now the max. Now we will see the main value function, main value. And what are the inputs of this function? B minus infinity plus infinity. State B minus infinity plus infinity. Just have a look once again. Maybe we have done some mistake. No, minus infinity plus infinity, that's okay. So this is the input to the main val. And that function has a statement. First, it has a terminal test check. So this is not a terminal state. So what is next? V is equal to plus infinity. That is something, the statement given in the pseudocode. After that, we have a for loop there. And after B, what are the actions available after B? B1, B2, B3. Okay, according to the diagram. So first we will execute this B1, and under this loop we have some statements in the algorithm as V is equal to main, V is equal to main, and then V is equal to max val. So this is again you are calling to that function, previous function, and then you have res S A, result of action A at state S. And then you have the values of for alpha and beta. And that's you are closing. And after that, you have some statements down here. If V less than or equal to alpha, then you have to return V, and then beta is equal to min, beta is equal to min beta comma V. And these three statements are again under this for loop in a similar way as I explained earlier. And then we have a statement return V out of this for loop. This is out of for. And now for B1, result state is result S, state is S, action is B1. At B, when you performed action A, B1, where you will reach, according to the diagram, you will reach at leaf node, and that leaf node has value 3. So I am writing the label, I am writing because there is no any name for that leaf node in the diagram. So I am writing that label or value as a name, for that. So I will reach at leaf node which has value 3. I'm not calculating the value. I'm just naming it with 3. Okay. Because I don't, otherwise you can write L1 or L2 or whatever. Just assume it a name and not a value. And then what is the value of alpha? What is the value of alpha? Value of alpha previously minus infinity plus infinity. So this is same. Minus infinity plus infinity. So marker is now dodging me. It is not supporting me fully. So 3 minus infinity plus infinity. This is the call to the Maxwell. Now this is the call to the Maxwell. So now you are going back again to that function with these values. 3 minus infinity plus infinity. So here you are calling this function with new values 3 minus infinity plus infinity. Okay, you are calling this function again with minus infinity and plus infinity. Okay, call it. Then now v is equal to minus infinity, and again for loop. It is not a, again this 3 is a leaf node. Yes, it is a leaf node. Thanks God. Otherwise I will do a mistake. There's no need to execute for loop and so on, because this 3, which I have given as a name for the leaf node. So this 3 is a leaf node. I can just show you. Otherwise, I said earlier that I will not show you the picture again. So just look over here. So I am here now at 3. 3, 12, 8. These are the 3 values. 2, 4, 6. These are the next values. This figure is better. A1, A2, A3, B1, B2, B3, C1, C2, C3, D1, D2, D3, 3, 12, 8. I don't have a name for these leaf nodes, so I am using this value as a name. 3, 12, 8, 2, 4, 6, 12, 14, 5, 2. So now I am stopping again. So 3 minus infinity plus infinity. According to the algorithm, we have a terminal. I can show you the algorithm also. Otherwise, you will not believe me. Because I know you all students. You are a non-believing generation. Sorry for these words, but I have only these words to say to you. Otherwise, you normally don't give me time. You don't give me, the common word is lift. You, you normally don't give me a lift, or you don't give me the value. You don't valued me. So I have only these words to tease you. So anyhow, to do fun with you. So now you are seeing this screen, and here we have a terminal test in the max value and also in the min value. We have this terminal. If it is a terminal state, then return the utility value of that state. And you are returning and you are exiting this, and you are exiting this function, exiting here at return v, where v greater than beta if condition, and also this return v, which is also making you to do an exit at this function. These same options are available for this thing also. And now I am again stopping sharing. So this is your, when you call this max value, this 3 is a leaf node. So you will return the utility value of this state. You will return the utility value. When you will return this utility value, you will come back here. This is the max value you call with this value. So you will, so these values has no importance. This value is returned. Max value, this value 3 is returned. Okay, this whole statement, or you can say this whole thing is now giving you 3, and this v is what? V is positive infinity. I can write it here, otherwise it will be an issue. V is what? V is positive infinity. And here what you will get? 3 by this max value function. So positive infinity and 3. What is the minimum? This 3 is minimum. So now V is, so now your V is, so now your V is what? You're now, sorry. So your V is now 3. So your V is now 3. Okay. When your V is 3, now you are going here. If V, which is 3, less than or equal to alpha, alpha is what? Alpha has the value minus infinity here from previous statement, minus infinity. Minus infinity. 3 less than minus infinity are equal to minus, no, minus infinity is something very much lesser. So this statement will not execute. And you will come here, next statement. And then is here, then return V. This is something, then return V. I'm not executing. So beta is then min beta. Beta. What is the value of beta? Value of beta is plus infinity. Plus infinity is the value of beta. And V is what? 3. Plus infinity and 3. What is minimum? Minimum is 3. Minimum is 3. So so the value of beta is 3 now. I can write this pair here, or you can, for example, plus infinity beta value, and this is 3. And I will get 3 here. And after that, what you have to do? This was the B1. The next step is performing that. These 3 statements are under this for loop. And now the next is you have to perform that action B2 according to that for loop. Okay. What is the value of V now? V has the value now. I can see 3 according to the previous statement. according to the previous statement. I can, for example, remove these values. Yes, I think I have the value of beta here and the value of okay. Now state is B, action is B1. By performing B1, I will go to another leaf node that is 12. 3, 12 and 8 are the three first leaf nodes. So I will reach where this is 12. So I am writing it here. So 12. And then what is the value for alpha? Value of alpha is remaining the same, which is minus infinity. But value of beta has been changed here. Value of beta, no, yes. Value of beta is changed here as 3. And you are calling this max value function. You are calling this max value function at the previous page. At the previous page. At the opposite screen, sorry, opposite page of this, opposite side of this whiteboard. So now you are calling this function maxval with values 12, minus infinity and 3. So I can write these values 12, minus infinity and 3. I can write these values here. Or I can also write it here, but okay, that's fine. So V is now again minus infinity. V is again minus infinity. For loop. No, for loop is not needed because this is the leaf node. And when it is leaf node, so you have to return the utility value of that leaf node and it will not be executed, this next statements, in a similar way as you have done for 3. So this is the 12 is the leaf node. When it is a leaf node, return the utility of that state and you will come out of this maxval function. You will come out. So 12 is now returned. 12 is returned. 12. So this is 12 and this is 3 and you have to return the minimum, which is 3. So you are not accepting this 12. So you can understand that the min player is not accepting this 12, which is even larger. So min has to accept the minimum value. So that is already 3. So this is 12, this is 3. So what is the minimum? 3. And you are updating this 3 up here. Again, it's again 3 here. Again, you are checking 3 is less than or equal to minus infinity. Alpha is minus infinity. Alpha is minus infinity. I can write it here. So 3, V is 3, 3 less than minus infinity, no, false. So you will come here, beta, min, and again beta and V. What is the value of beta? Value of beta is now 3, okay? It is not something positive infinity. Value of beta is now 3. You can see it from here also. And the value of V is again 3. And 3, 3, what is the minimum? And from this 3 and this 3, what is the minimum? 3. So the value of beta is again 3. And it is something, these 3 statements are under this loop. So you are now executing B3. B3 is reaching where? B3 is the edge which is going from the state B to the next state, which is 8, which is a leaf node. Okay, we'll see. So my V is now 3. And you are again calling this maxval function with these values. From B, state is B, action is B3, you are approaching at 12, 8, sorry. You are approaching at 8, so I am now deleting it. And I am writing 8. So this is 8. And alpha is what? Alpha. Alpha is minus infinity, no change. Beta is what? Beta is 3. And you are calling this max value function at the backside. With the value not 12, rather it is 8. So I have changed this value. 8 minus infinity 3. So these are the values. 8 minus infinity 3. You are calling it, this 8 is this is the state. This 8 is state. So this is terminal state. So it will be checked and you will return the utility value. Very first statement of this pseudocode, not mentioned here. You can see it by yourself in the previous moments of this lecture. So you will return the utility value and it will be 8 actually. So this value will come here as an 8 and this is 8 and this v is 3 and you have to take the minimum. So what is the minimum? 3. So the value of 3 will remain 3 as it is. 3 less than minus infinity? No, it is false. So I will come here. So I will come here. Next pair is again value of beta is 3, value of v is 3, so minimum is 3. So no change. No change. Okay. Now this loop has been ended. These 3 statements are under this loop, but now this loop has been ended. And if this loop has been ended, what is the next statement? Next statement is return v. What is the value of v? Value of v is 3. So you will return v, min value. So this is the function min value. So now you will come back here. So min value. So this was the first call. You can see b, node b with minus infinity plus infinity. Okay, and this was the call, and it is giving you 3. It is returning from here, from this side. And this was the first execution of this Maxwell function. First execution. And with this first execution, you can imagine that you have processed only the first part, first branch of, or you can say the first subtree of the node A. Okay. So I am stopping it here because I have to do the aftar, and then after aftar I will come back again. I will come back and I will start from here. This is my, for example, this is my mark to start. So I am stopping this recording and I will come back. Okay, so I am here at this value which I have highlighted. So this main value function return 3, and this return 3 will come here, and from this 3 and this minus v minus infinity value of v, what is the maximum? The maximum value between these 3 and minus infinity is 3. This is the maximum value. This maximum value will come here, will become the value of 3 here. So now I have to check if this 3 greater than beta. What is the value of beta? Value of beta is plus infinity. So 3 is greater than plus infinity. 3 is greater than plus infinity? No. So I will come here at this alpha. And it will be checked here that what is the value of alpha? Alpha is, you have to check that alpha is minus infinity. Alpha is minus infinity. And beta is max alpha and v, alpha comma beta. Here I have to check it is, maybe I have written it wrongly. So this is max value, alpha and v. So this should be v. This should be v. So alpha is minus infinity and v is 3. And from this pair, what is the maximum value? Maximum value is 3. So alpha becomes 3 here. Alpha becomes 3 here. And as these 3 statements are under this for loop, so action A1 is now completed, and now I have to perform action A2. So action A2, by performing this action A2, we will reach at node C. So what is the next statement? This is not a terminal state. C is not a terminal state, so this statement will be executed. And max v, what is the value of v? It is not minus infinity. It is now 3. So I have to update this value as 3. So just a minute, I have to take my glasses. So this v is 3 now, and I have to call this main val function, which is at the backside, and result from state is what? State is C. So from A, after applying action A2, I will reach at C. And then comma alpha. Alpha is what? Alpha has the value 3. So alpha has the value 3. Comma beta. What is the value of beta? Beta has the value positive infinity as it is. So this is now, you can see C. So min value function will be called with C3 and plus infinity. So this is the min value function. I have to call this function min value. Min value node is C. Alpha has the value 3 and plus infinity. So C and then 3 and plus infinity for the B value. So C3 and plus infinity. So this function will be called. This C is not the terminal node. So okay, so then I have to, then V is plus infinity again. and I have to execute this loop again, which is not for B1, B2 and B3, rather now it will be executed for C1, C2 and C3. And I have to execute it for C1. So for C1, now V is again, now because I am executing it again for the first time, so V is now plus infinity. So I have to write it plus infinity. And then Maxwell, result from state is C. At C, when I will perform this action C1, where I will reach at leaf node, which has the value 2. So result SA will produce what? 2 will produce 2, and then value of alpha. Value of alpha is 3. So I have to write 3, and then value of beta is plus infinity. So Maxwell function will be called with these 3 values, 2, 3 and plus infinity. So I have to come here again at this. And it will be called with I can write it here. It will be called with 2, 3 plus infinity. 2, 3 and plus infinity. It will be called with this value. This is now finished. This is now finished. So 2, 3 and plus infinity, it will be called. This 2 is a terminal state. So the utility value of this state 2 will be returned, and this whole for loop another will not be executed. So 2 will be returned. So I will come here. So this will be returned with 2. So max value function, after executing this one, it will give me 2. So 2 and plus infinity. What is the minimum? 2 is the minimum. 2 is the minimum, so the value of V will be updated with 2. Now I will come here. If 2 is less than alpha, value of alpha is what? Value of alpha is 3. Value of alpha is, as you can see, value of alpha is 3. So 2 less than or equal to 3, condition true. Condition true. When it is true, then return V, and this next statement will not be executed because now you are exiting from this main value function. So return V. V is what? 2. So now you are exiting from this function, and you are not executing these edges C2 and C3. So this is that pruning. So this is that pruning element. Now you are filtering. And this condition is for the pruning. If V less than or equal to alpha, then return V. So this condition is for that pruning procedure. So when you will return V from here, which is true, which is which is 2, then you are coming back again here. Here you called the main value. Here you called the min value function. Just a moment, because I am just taking some time. C3 plus infinity. And you are executing with these values 2 and then return V. So here, when this main value function gives you to return, because when you said here, when this statement executed 2 less than or equal to 3, the condition is true, then return this V, which is 2, and you are exiting this main value function. So you are giving this value back here at this position, and you are getting 2 here. So 2 and this value is 3. What is the maximum? Maximum is 3. So the value of V is becoming 3 now. And after that, you have to check that this 3, this is the value of 3. So this is 3. 3 greater than or equal to beta. What is the value of beta? Value of beta is plus infinity. Plus infinity. And 3 is here. 3 greater than? No, condition false. You will come here. And it is written here max alpha comma V. And the next pair that you have to check, alpha is what? Alpha is 3. And V is what? It is 3. So from this pair, what is the maximum? Maximum is 3, so the value of alpha is still remaining 3. And now it is finished, and now you are executing A3. And you have seen that this C1 and C2 and C3 are not being checked, and it is pruned away. And now you are going directly to another edge, that is A3. Okay, A3, action A3 will give you access to node D. And after that, you have the value of V as 3, previous main value, and result from state A. And after performing action A3, you will reach at node D. You will reach at node D. And what is the value of alpha? Value of alpha is 3. So you can write it here. And what is the value of beta? The value of beta is again similar, plus infinity, according to this algorithm, the previous state. And now you are calling min value function. Min value function D3 and plus infinity. Min value function is this one. And now you can write it here. So now node is D3 plus infinity, and then 3, and then plus infinity. So now you are calling this min value function with this one, according to the backside of this board. When you are calling, it is not a terminal state, and then V is equal to plus infinity, that's okay. And then you have to perform this for loop again for this node D. And on this node D, what are the operations available? D1, D2, and D3. So now you have to perform this for D1, D2, and for D1, D2 and D3. Okay, now first you have to perform D1 and then min V is what previously, now you are coming for the first time, so V is plus infinity and max value. So this would be the similar. For what are the states available here? What are the states available here? 14, 5 and 2. 14, 5 and 2. So 14, 5 and 2. This is 14, this is 5 and this is 2. And all these operations will be performed very much similar to B1, B2 and B3 in the same way. Only this C1, C2 and C3 are pruned away. These are the two branches that are not checked by this alpha beta pruning algorithm. Rest of the branches, even this 14, 5 and 2 will be checked accordingly. And I am leaving it to you so you can calculate it by yourself. So this is basically the alpha beta pruning algorithm. And here we are coming, in previous step we are coming with this 2, but this 2 is not needed because 3 is already the options. And now I can go back to that slide from which you can get further information. So now focus on this slide. This is the output of that alpha beta pruning algorithm that we were performing on the board. So here, this is the A, and this is the max call, and it was A1, A2, and A3. First, it is A1, and when it reaches at B, then it is the call for the min value, and then it is B1, B2, and B3. First, it is with the leaf node 3, and the value of B3 is updated as a beta value. After that, when it will open up another leaf node with value 12, it will not update the value because the min, because this is the lever for the min, and min forced the value of beta to remain as 3 because this 12 is greater, and the min player didn't want to give this highest value to this max player. And similar is the case with the 8. And from these 3, 12 and 8, 3 is the minimum. So this min player will give this 3 to this beta value. And this, after opening up all these branches, this minimum value will become the alpha value, which you can propagate further at higher level for the max player. And that's why you are seeing that alpha is also getting this value 3 as allowed by this min player. Similarly, after that, when you open up this node C, after opening this first branch, which is 2, the value of B is updated here. And this 2 is minimum from this 3. And max player don't want to get this minimum value because max has already 3 alpha value as a higher value. And if your max player will not accept this 2, then there is no need to open up these 2 edges. And that's why it was skipped in the algorithm, and then you will come to this branch. And when you will open up 14, the beta value with 14 is updated, and also this max player wants this value, but here 2 edges are remaining. Min will not allow this 14 to go at higher level until it open up all the
branches. So that's why the main player will open up then next 5, and it will update the value of beta as a 5 here. And when it will open up this 2, it will update the value of beta 2 here. And now this 2 is not needed to this max player, because max is already achieving this 3 value for the alpha. So this value for the beta, which is updated here at this level, um, also for the alpha, which is 2, is not acceptable for this max player. That's why it is mentioned here that the beta value is 3 at the root and the alpha value is 3 at the root, which you have seen when I was performing on the whiteboard. So this is the output of this alpha beta pruning algorithm. And now this is the lab project number 7. What you have to do, you have to implement this basic tic-tac-toe game using this adversarial searching algorithm. Any other adversarial searches algorithm you can use. You can use simple minimax, and you can also use alpha beta pruning. So you have to visit this link, and then you will find some source code here. You have to download it, you have to configure and execute it on your machines, and after getting understanding, you have to submit the final reports. So this is the end of the chapter. And now maybe you have seen the university notifications that the examination will be uh, held in the month of maybe July, I think, maybe. Yes, if I am not wrong. I will provide you that notification. So now your course is completed, and the other thing is that on your Google Classrooms, you have to submit your all lab projects with these reports. Thank you, and we will see soon, inshallah, after the end of this COVID pandemic in proper classroom environment. Thank you very much.